So this week we are going to discuss dynamic scheduling and the Superscalar Organization, which consists of various microarchitectural components that help in achieving dynamic scheduling. And in this module, we are mainly concentrating on Superscalar Organization and discuss various components in the Superscalar processor. So we know that the in-order execution will degrade the performance. The reason is if the leading instruction is stalled, even though the trailing instructions are independent, we cannot issue these trailing instructions to the functional units, and as a result the overall performance will be degraded. So in other words, the in-order instruction issue and execution will degrade the performance, and we need to look at some other alternatives to improve the overall performance. So when we move from scalar pipeline design to superscalar pipeline design, we can issue multiple instructions, we can fetch multiple instructions, we can decode multiple instructions, and we also have the support for multiple execution units in a superscalar pipeline design. And once we have the superscalar processor, in order to expose the instruction level parallelization, we can take the help of either the compiler or the hardware. And we already discussed various compiler optimization techniques to expose instruction level parallelization. And now in this week we are going to discuss the hardware techniques that will expose instruction level parallelization to the underlying processor, that is superscalar processor, so that the performance can be improved. So in order to overcome the performance penalty associated with the in-order execution, we are now going to the out-of-order execution, and to execute instructions in an out-of-order fashion, so we need the support from the superscalar processor. And so as part of this dynamic scheduling, we are going to discuss various techniques associated with the out-of-order execution of instructions. So we already discussed in the previous modules that the instruction dependencies will limit the execution of instructions in an out-of-order fashion. So instruction dependencies consists of data dependencies and name dependencies. And the data dependencies are the dependencies where actually the true dependence will be there, because the true data flow will happen between producer and the consumer. But whereas in the case of name dependencies, when instructions have name dependencies, there is no flow of information between producer and consumer, and this also called as the false dependence. So in order to eliminate the false dependence, we have to use techniques such as register renaming. So as part of this dynamic scheduling mechanisms, we consider techniques to eliminate these false dependencies by using register renaming. And once we eliminate name dependencies or false dependencies, so as a result we can schedule instructions in an out-of-order fashion. So we already discussed in the compiler optimizations that the instructions at compile time can be rearranged in such a way that if the rearrangement of instructions are not going to create any data flow or exception behaviors, then we are fine with the rearrangement and then execute these instructions in an out-of-order fashion. So as long as we take care of data flow and the exception behavior, we can rearrange the instructions at runtime after identifying that the instructions are independent, and then schedule these instructions onto functional units so that we can parallelize our execution, or we can overlap execution of multiple instructions and improve the overall performance. So the main advantages with the dynamic scheduling compared to static scheduling are: the dynamic scheduling allows the code compiled for one microarchitecture to run efficiently on another microarchitecture. We know that for the same ISA we can have multiple microarchitectures. So for example, the AMD processor and Intel processors can use the same ISA, x86 ISA, but the way the processor designed in AMD can be completely different from the way the processor designed by Intel. A single ISA can be realized through multiple implementations, and each implementation is corresponding to one microarchitecture, so that we can have multiple microarchitectures which have the same underlying ISA. So when I say multiple microarchitecture for the same ISA, one processor may consider 5-stage pipeline, the other processor may consider 10-stage pipeline, and one processor may consider single ported register file, the other processor may consider multi-ported register file. One processor may consider a single issue, the other processor may consider multiple issue. So we can have several variations in our microarchitecture, but the underlying ISA can be same. As long as ISA is same, the code which is written based on that particular ISA can be executed on any of the microarchitectures or any of the processors. And once we have the dynamic scheduling support in our system, so as a result we can efficiently execute a code which is based on the same ISA on various microarchitectures. And the second advantage with the dynamic scheduling is, so it handles the dependencies that may not be known at compile time. And the third advantage with the dynamic scheduling is the processor can tolerate unpredictable delays. So in order to understand the dynamic scheduling part, let us focus on the Superscalar processor organization in this module. So once we have the thorough understanding of Superscalar processor organization, then we can apply the dynamic scheduling mechanisms to expose significant instruction level parallelization that is present in our programs, so that we can improve the overall performance of system. So we start with the Superscalar processor organization. So this consists of several pipeline stages, starting with the fetch stage. So in the fetch stage, we fetch multiple instructions from the instruction cache, and all these fetched instructions will be stored in the instruction decode buffer. This is a buffer which is placed between instruction fetch and the instruction decode. And once we fetch the instruction and stored in the intermediate buffer or the pipeline buffer, we take these instructions and give it to the decoder, and decoder decodes all these instructions simultaneously. So effectively we have support for multiple instructions decoding in the decode stage. After the decoding is done, we dispatch these instructions through a dispatch stage, and the main idea of the dispatch stage is the instructions will be dispatched to the functional units. In some processors, they combine the dispatch buffer and the reservation station together, and whereas in some designs they separate the dispatch buffer and the reservation stations. So again, there are advantages and disadvantages with each of these designs, but in this particular organization what we are considering is, after dispatching, these instructions will be moved to a different reservation stations, and we have one reservation station for each of the functional unit. So we know that after decoding the instruction, the type of instruction what we are going to execute, and based on the type of the instruction, we dispatch this decoded instruction to the respective the reservation station. And in this particular design, we are considering separate reservation stations for each of the functional units, but there are designs where they consider a single reservation station for all the functional units. We are going to discuss that in the next file. So once the instructions are stored in the reservation station, if the operands are ready and if the functional unit is free, then we can schedule one instruction at a time from the reservation station to the corresponding functional unit. And here again, selecting one instruction from a set of instructions that are stored in the reservation station, we can apply various heuristic mechanisms. We can consider an out of order the selection of instructions from this reservation station. So that's the reason why, if you see in this Superscalar processor organization, the fetch stage decode stage and the dispatch stage are actually working in the in order fashion, but whereas the selection of instructions from the reservation station to be issued to the functional units happen in the out of order fashion, and the execution of these instructions happen in the out of order fashion on the functional units, and finally depending on the type of the instruction, depending on the number of cycles the instruction is going to take for executing, these executed instructions will be returned to the buffer that is called as a reorder buffer in out of order fashion. So effectively, so starting from the reservation station output to the reorder buffer input, we have out of order flow in our instruction execution. And once we have instructions executed by different functional units and returned to the reorder buffer, we select instructions from this reorder buffer and will complete these instructions in the program order again. And some instructions, when we have memory instructions, typically store instructions, then we need one more stage after the complete stage, that is called as a retire stage. So the complete stage is the stage where all the ALU operations and the load operations will be completed, will complete their execution. But whereas for the store instructions, after completion stage, the stored values will be returned to the store buffer, and the actual write operation to the memory happens only in the retire stage. We already know that for a store operation, if you are going to wait till the time when the store operation is writing to the memory, it is going to take significant amount of time, and if you are waiting for so long time, then it is going to degrade the performance. So as a result, in order to minimize the penalty associated with store operations, we typically consider a store buffer where after the completion stage of the store instruction, we write to the store buffer, and so that this store operation is said to be completed from the processor point of view, but the actual operation of actual write operation happens only in the next stage, that is the retirement stage. But for all other operations which are ALU operations or the load operations, because we are not going to write to the memory, so we can complete the execution of these operations at the end of the complete stage. So when we say ALU operation or load operation is completed, we are actually writing to the architectural registers of the processor, and writing to the architectural register happens at the end of the complete stage. So each of these pipeline stages in the superscalar processor has a specific role to play. The fetch stage is going to fetch the instructions, the decode stage is going to decode the instructions, dispatch stage is going to dispatch the instructions to various functional units or associated reservation stations, and reservation station keep all the instructions which are waiting to be executed by the functional units, are waiting for the operands to be available, and the execute stage actually performs the actual execution of the instructions on different functional units. The complete stage is going to complete the processing of the instruction from the mission architecture point of view, and the retirement stage is the stage where we actually write the store values from the store buffer to the memory. So out of all these stages, the fetch, decode and dispatch, we follow the program order, and for the completion stage and the retirement stage, we follow the in order or the program order again, but for the execute stage we will go by the out of order fashion. So because we can exploit the instruction level parallelization at the execute stage, that is mainly because our processor may have multiple functional units and there may be independent instructions in the program, and as long as the independent instruction is there and the function is available, we can schedule these independent instructions in an out of order fashion, and we can execute them on the functional unit so that the execution of different instructions can be overlapped. In other words, we can exploit the parallelization of the independent instruction execution using this various execution units, and that will improve the overall performance. And we need in-order completion and in-order retirement. This is required mainly to maintain the correctness of the program. So when we are going for the in-order commit, so as a result what happens is, even if the leading instruction is creating an exception, we are not committing any of the trailing instructions, so we save the processor, we save the process state, and we re-execute the instructions starting from that accepting instruction. So having discussed this superscalar the processor organization, now we are going to look at some of these stages thoroughly, and we start with the dispatch stage. So the main role of the dispatch stage is, it has to route decoded instructions to the appropriate functional units, because after the decoding we have the decoded instructions, and we also know the type of instructions what we are going to execute. So the dispatch stage is going to dispatch these instructions to appropriate functional units. Either it can directly issue the functional unit, or we may consider a design where it will be issued to the reservation station, and from the reservation station we can issue to the functional unit. So when we consider a system where if you are dispatching the instructions directly to the functional unit, then our dispatch and the issue both will be same. But in some designs they consider a separate stage in between the dispatch and the functional unit execution, so that is called as a reservation station. There dispatch means dispatching to the reservation station, and issue means selecting an instruction from the reservation station and giving it to the functional unit. The main role of the reservation station is to decouple the instruction decoding and the instruction execution. So once we decouple the instruction decoding and the instruction execution, so we can eliminate the stalls at the instruction decoding stage, as well as the penalties at the, or the starvation at the instruction execution stage. The main role of reservation station is dispatching the instructions from the decode stage to the one of the entries in the reservation station, and the second role of reservation station is to keep all the non-ready operations, non-ready instructions to be waiting in the reservation station itself, and the third one is select one ready instruction from the list of instructions that are there in the reservation station to be issued to the functional unit. In order to do these three tasks, our reservation station will be designed like this. It consists of multiple entries, and it has allocate unit, issue unit, and the set of fields in each of the entries. Whenever an instruction is decoded, and this instruction needs to be dispatched to the reservation station. So in order to dispatch the instruction to a reservation station, all we have to do is we have to check whether there is a free entry in the reservation station. So as a result, this allocate unit is going to scan through all the entries in the reservation station to see if there is a free entry. So this can be identified by using a single bit information per entry, and that is called as a busy bit. Whenever we issue an instruction, whenever we dispatch an instruction to the reservation station, we set the busy bit of the corresponding entry, so that next time if any other decoded instruction to be dispatched to the reservation station, we are not going to write that decoded instruction into this entry. So as a result, we are not going to overwrite the existing data with the new data as long as if the busy bit is set. So The allocate unit always scan through all the entries of the reservation station and identify the free entry which is specified by the busy bit, that is a reset, and once we identify a free entry, we dispatch the decoded instruction into that particular entry. At the time of dispatching an instruction to the reservation station, the operands may not be available. So, sometimes all the operands are available at the dispatch time, sometimes a partial operands are available, and in other times none of the operands are available. So, as a result, if the instruction whose operands are not ready at the time of dispatch, we have to send the register tag to the reservation station, so that whenever the producer instruction produces the value to the corresponding register, we can send the data to the waiting instruction that is stored in the reservation station. Instructions will be waiting in the reservation station to be selected by the issue unit, and we know that each instruction will have two source operands, and if both the operands are ready, then we set the ready bit associated with that particular entry. And the issue unit is always going to scan through all the ready bits of these entries in the reservation station, and it can select one instruction from all the ready instructions, and this selected instruction will be issued to the functional unit. So, that is the role of this issue unit. So, the allocate unit always keep track of busy bits to identify a free entry in the reservation station, and the issue unit always keep track of ready bits to identify the ready instruction to be issued to the execute stage. And if the instructions are not having their operands ready, then they will be just waiting in the reservation station itself. So, each entry of this reservation station will look like this. It consists of a busy bit, operand 1, a valid bit, operand 2, valid bit, and ready. So, here as soon as an instruction is dispatched to an entry, we set the busy bit, and this operand 1 is the source operand 1 for the instruction, and if the operand is already sent, or if the operand is available, or the operand is ready, then we set the valid bit, and if the operand is not available at the time of dispatch to the reservation station, so we reset this bit, and if both these valid bits are set, that indicates that two operands for this instruction are ready, and then we set the ready bit, so that the issue stage will keep track of this, and it can select this instruction to be issued to the functional unit. And we already discussed in the previous modules that in order to improve the overall performance, or in order to minimize the stalls because of the dependencies, as soon as the operands are produced by the functional units, we can forward these operands to the dependent instructions. So, in order to support that operand forwarding, so what we do is, for this reservation station, we have a connecting paths from the output of the functional unit to the inputs of each of these entries. So, here we have forwarding slots, and whenever a functional unit executes or completes its execution, it forwards the computed value back to this reservation station. Along with this computed value, it also forwards the tag associated with the operand. In other words, we forward the register tag as well as the computed value that is going to be stored in the register. And using these forwarding slots, we compare the tags of this computed value with the tags of the operands that are stored in the reservation station. If there is a match, we are going to write the computed value onto that location, and we set the corresponding valid bit, so that this value is available in the reservation station, and next time when both the operands are ready, then we can issue this instruction to the functional unit. And also, so here we have support for the dispatch slots, because whenever as soon as we decode the instructions, we have to dispatch this instruction to the reservation station And so as a result, this dispatch slot is actually going to take care of that, where to dispatch or which entry the decoded instruction to be dispatched. So that will be taken care by this dispatch slots, and whenever the value is computed by the functional unit, this forwarding slots is going to take care of forwarding that value to the to a particular entry in the reservation station. We know that if the functional unit is not available, a reservation station is not going to issue an instruction to the functional unit, even though the operands are available. So in other words, because there is no availability of a free functional unit, we are not issuing the instructions to that functional unit. So that indicates that the reservation station can take care of structural hazards properly. And similarly, if the operands are not available, even though the functional unit is available, we are not going to issue this instruction to the functional unit. That indicates that this reservation station is taking care of the proper data flow, or otherwise this reservation station is taking care of the read after write hazards. So the reservation station can be implemented in a centralized way or a distributed way. In the case of centralized reservation station, which is typically implemented in Intel based the processors, especially this example is for the Intel Pentium Pro, so which has a centralized reservation station. So once we have a centralized reservation station, so we combine our dispatch stage as well as the reservation station together. So the decoded instructions will be dispatched to the dispatch buffer, and from this dispatch buffer instructions will be selected and they sent to the execute stage. So here the input to the dispatch buffer is coming from the decode stage in order, but the output from this dispatch buffer is going to the functional units in the out of order fashion. And the main advantage with the centralized reservation station is that we can utilize the entries in the reservation station efficiently. And also because here we have a combined stage for both the dispatch and the reservation station together. So as a result, the input side of this dispatch buffer is called as a dispatch operation, and the output side of this dispatch buffer is called as the issue stage, or we can interchangeably use the dispatch and the issue, especially when we are dealing with the centralized reservation stations. And but the main disadvantage with the centralized reservation station is whenever we want to select a ready instruction from this entire list of instructions that are stored in the reservation station, we have to scan through all the entries, and that is actually going to consume significant amount of time as well as the power, because we know that here in this particular design we have 4 functional units, and each of these functional units may require one instruction in a cycle. So in other words, in a single cycle we may have to dispatch 4 instructions from this dispatch buffer to all these functional units. So in order to support that, we need to have multi-ported dispatch buffer from at the output side. So we need to have 4 ports so that 4 instructions can be issued or dispatched to the execute stage. And we already discussed in the cache memory design, once we have increased number of ports, it is going to increase the overall execution time, and also it is going to incur the hardware overhead as well as the power consumption. So as a result, in order to eliminate the problems with this centralized reservation station, we can go for other alternative where we have a separate dispatch buffer and then we have a reservation station separately. The output from the decode stage will be written to the dispatch buffer, and from this dispatch buffer we are going to dispatch instructions to different functional units depending on the type of the instruction. And here in this particular design we are considering one reservation station for each functional unit. And so as a result, whenever we want to issue an instruction to a functional unit, all we have to do is we have to search only in the limited entry reservation station, and each of the reservation station requires only a single port. So compared to this centralized reservation station, the entries in the distributed reservation station may not be utilized efficiently, but because we are going to have only single ported reservation stations for each of these functional units, the access time will not be significant. So effectively there is a trade-off. So whether we want to efficiently utilize all the entries in the reservation station, or whether we want to have lesser access latency to select an instruction from the reservation station. This type of distributed reservation station is implemented in IBM PowerPC. But note that these two are two extremes of the designs. One is using the complete centralized reservation station, the other one is using a complete distributed reservation stations. But as an intermediate to these two designs, we can come up with the clustered reservation stations, where rather than having one reservation station per functional unit, or rather than having a single reservation station for all the functional units, we can cluster or we can divide the reservation station into multiple clusters, and each cluster can feed in multiple functional units associated with that. So in other words, we can consider an intermediate design where this reservation station is divided into two sub reservation stations, and one reservation station will take care of supplying the instruction to these two functional units, and the other reservation station can supply the instruction to the other two functional units. So again, because the whole computer architecture is a design space exploration, so we can come up with an efficient reservation station which is not going to underutilize the space in the reservation station, at the same time is not going to consume the significant access latency and the area overhead. So as I mentioned earlier, so the centralized reservation station can utilize the space efficiently, but the distributed reservation station will have low access latency because of single ported design we consider. So having discussed this reservation station, now we will move on to the reorder buffer. The reorder buffer is required whenever we are supporting the out of order execution in our the system. So before that, we will define what is an in-flight instruction. An instruction that is dispatched to the reservation station, and the instruction that is there in the functional units, or the instructions which are finished their execution but not yet returned to the architectural registers, are called as in-flight instructions. And for each of these instructions, we are going to maintain an entry in a table, and that table is called as a reorder buffer. And we know that only finished and non-speculative instructions can be completed. When I say finished, an instruction finishes its execution. For example, when I give an add instruction, add R1, R2, R3, so performing of the add operation on R2, R3 contents, if it is done, then we say this add instruction is finished its execution. But when we write the final value to the register R1, then we say that this add instruction is completed. Because of out of order execution, a trailing instruction may finish its execution, but it is waiting for all the leading instructions to be completed, then only this instruction will complete, will write to the architectural registers. We can complete only those instructions which are finished their execution, and those instructions which are issued in non-speculative way. In order to enforce this constraint, and also at the same time in order to provide out of order execution, we are going to use a buffer called as a reorder buffer. And a reorder buffer is implemented as a circular queue which consists of multiple entries, and when an instruction is dispatched to the reservation station, we allocate an entry in the reorder buffer. And each entry in the reorder buffer consists of multiple fields. One is the busy bit. This is going to say whether the entry is allocated to an instruction or not. So there is a second field that is called as issued, and this is going to specify whether the instruction is issued to the functional unit or not. A finished field is there, which is going to specify that whether the instruction is finished its execution or not. And there is a field in the entry that is going to store instruction address, and also we have a rename register for each of the operands in our instruction, because we know that the register renaming is used to eliminate the name dependencies, and register renaming is one of the main components in our dynamic scheduling. So as a result, our reorder buffer also has an entry associated with the rename register. And sometimes we issue instructions with some speculation or by predicting something is going to happen. So all the instructions which are issued in a speculative way, we have to set the corresponding bit in an entry. So for that we will have speculative field in our entry, and also we have a valid the field. So this valid field is going to specify whether the instruction is valid to be completed or not. Sometimes what happens is, because of some exceptions and so on, we may have to invalidate all the entries. So in those cases we require a separate field in our for each entry in the reorder buffer, and that is the reason why we consider this valid bit. Effectively, each entry consists of multiple fields, and each field is going to do a specific task. And whenever we are going to dispatch an instruction to the reservation station, we have to see whether there is a free entry in the reorder buffer. So that will be indicated by this busy bit. If the busy bit for an entry is reset, then we can select that entry and we store the instruction in that particular entry. And once we store the instruction in that, then we move this tail pointer towards left, so that it will point to the next free entry in the reorder buffer. Because we are implementing this as a circular queue, so this tail pointer will be advanced towards left whenever we are inserting new instruction into an entry, and the completion of instructions will happen only in the in order, that is in the program order. So in order to ensure the in order commit, we are going to commit only from the head pointer side, that is from this side. So the head pointer pointing to the next instruction that is going to be completed, and once this instruction is selected and moves to the commit stage or a complete stage, we can advance this head pointer towards left, so that it is pointing to the next ready instruction, next instruction in the sequence to be committed. And all these instructions which are there between this head pointer to the tail pointer are called as in-flight instructions, because we know that these instructions will be there in different hardware components in our superscalar processor. Either they will be there waiting in the reservation station, or they will be executed by the functional units, or they will be just finish their execution but not at the completed their commit stage. So these are called as in-flight instructions, and for all the in-flight instructions we are going to have one entry in our reorder buffer. And using this reorder buffer will ensure in order commit, so that the program correctness is maintained even when there is an the interrupt happens, or even when there is an exception happens. With the help of this reorder buffer, we can execute instructions in an out of order fashion without creating any program incorrectness. When we are issuing any instruction in a speculative way, we have to set the speculative bit, but after some time the speculation is resolved. That means, like for example, for a control instruction we predict that the branch is going to take place, and we dispatch the instructions in the predicted path. So all these instructions which are dispatched in the predicted path, we have to set the speculative bit 1, and after some time the branch condition is resolved, and if our prediction is correct, that means whatever we speculated earlier is actually correct, then in that case we have to reset all these speculative bits associated with these instructions which are dispatched in the speculative way. So those things will be reset so that these instructions can be committed once they finish their execution. So that means like whenever we are going to select an instruction pointed by this head pointer from the reorder buffer to complete, we have to ensure that the speculative bit for that instruction is reset and also the valid bit is set, and also whose finished bit is also set, because there may be a scenario where instruction can come to the head of this ROB, but the instruction is not yet finished its computation. If it is so, its finished bit is set to be 0. So as a result we cannot proceed with this, and even when there is a trailing instruction which finishes its execution, we cannot commit this second instruction unless the first instruction is the completed. So because of this restriction we are able to complete the execution, we are able to ensure the in order commit. And so as a result, like in the entire superscalar processor design, there are 3 important components. One is reservation station, the second one is a reorder buffer, and the third one is a dynamic execution core that we are going to discuss in the coming modules. And these are the 3 critical components in our superscalar processor to enable the dynamic scheduling. Finally, so we have this completion stage. So this completion stage will finish the execution of an instruction and update the mission state. So if I consider an example, add R1, R2, R3, where R2, R3 are source operands and R1 is the destination operand. So once the add operation is finished, then the instruction is said to be finished its execution, and when we write the value to the architectural register, that is R1, then we say that this instruction is completed. When we update the architectural register with the computed value, then this instruction is said to be completed. In other words, when we are writing to the destination register, then we are actually updating the mission state, and once the commit is done, we cannot recover the previous state. So after the commit is done, we overwrite the earlier content that is stored in R1 with the new content, and once the overwriting is done, we cannot recover the earlier data that was stored in R1. So that's the reason why whenever we are going to complete an instruction, we have to ensure that this completion is not going to create any problem with the mission state. So that means like unless we are sure that the instruction is needed to be completed, we have to keep that instruction waiting. Once everything is taken care, once we know that once we are sure that we can go ahead with the completion of an instruction, then only we can proceed with the completion stage. If that is not the case, then we should not do that. So in other words, for example, if we issue an instruction in a speculative way and the speculation is not yet resolved, then we should not proceed with this instruction for the completion stage. If you do that, after completing a speculatively executed instruction, we update the mission state, that means we update the register content, and after that if we identify that our speculation is wrong, then we cannot revert the state back to the original state. So that is going to create problems. So that's the reason why we have to ensure that only the proper instructions will be going through the completion stage. So for that our reorder buffer will help in identifying the suitable instructions which can go through the completion stage. And all the ALU and the load instructions will go through this completion stage and will update the architectural registers. In other words, we also say that the mission state is updated. So by the way, a mission state is nothing but the state of all the contents of all the architectural registers and the contents of our program counter and other things. And we require this mission state whenever there is any exception happens or whenever there is any interrupt happens. We have to save this mission state so that when we resume the execution, then we have to execute from the proper state. So that's the reason why we need to remember this mission state. And for all the store instructions, we have to update the memory with the store instruction content, with the content specified in the store instruction. So we consider a separate the pipeline stage in our superscalar process, that is called as a retirement stage. And the retirement stage is for only the store instructions, and so this retirement stage will take the instruction from the store buffer and will be returned to the memory whenever the memory is free. We also know that among the load and store instructions, loads are critical for the performance point of view and the stores are not so critical. So as a result, whenever there is a contention for the memory to be used by both the loads and stores, we have to give priority for loads so that the processor will not be stalled for the load value, and it can improve the overall performance. And since we are giving importance for the load instructions when there is a load and a store instructions contending for the memory, so the store instruction will be writing to the store buffer, and from the architecture point of view we can say that the store is completed, but the actual data will be written to the memory only in the retirement stage. So in other words, a store may complete by writing to the store buffer, but it retires only when the data is written to the memory. So there may be several cycles between writing to the store buffer and writing to the memory, because the memory may be busy with dealing with the load instructions and so on. So as a result, we'll write all the contents of this store instructions to the store buffer as long as store buffer has enough entries. If the store buffer is full, then we have no other option. We have to take the control of the memory and write the data from the store buffer to the memory, so that we will get some free entries in the store buffer, and after that again we can give the control of this memory to the load instructions if there are any load instructions waiting to be serviced. And while we are executing the instructions, we may get an interrupt. Interrupt can be issued by the operating system or some other external device. So whenever there is an interrupt occurs, then we have to service, we have to take care of that interrupt. That is by executing the interrupt service routine associated with that particular interrupt. So effectively, whenever there is an interrupt occurs, we stop fetching the new instructions into the system, but we are not going to flush the pipeline stages, because different instructions may be there in the different hardware components, and all the in-flight instructions we are going to execute them completely, and then we start executing the interrupt service routine. Only when the in-flight instructions are completed their processing, then only we start servicing the processor interrupt service routine. And so that is again with the help of reorder buffer we are going to take care of this scenario, because we know that which instructions are in flight by using the reorder buffer. All the in-flight instructions are indicated by the pointers starting from the head pointer to the tail pointer in our ROB are the instructions which are in flight, and all these instructions we have to complete their execution. But we stop fetching the new instructions until we service our interrupt service routine. This is about the interruption, and this can happen because of an external event or the operating system will issue an interrupt. But there is another scenario where there is no external interrupt, but with the execution of an instruction we may get an exception. For example, when we are dealing with a floating point instruction, we may get an overflow, or when we are dealing with an ALU operation, we may have a divide by 0 exception. When we have such type of overflow, underflow, divide by 0 exceptions and so on, then we have to deal with those things in our execution of the program. So that is when an exception happens, the result of the computation may no longer be valid. And because we know that using the superscalar processors, we execute instructions in out of order fashion. So, when we are executing instructions in out of order fashion, a trailing instruction may be executed before the leading instructions, and this trailing instruction may create an exception such as divide by 0. When such things happen, then we need to recover the state of the mission, or we need to restore the proper state of the mission, or we need to go back to the proper state of the mission before the execution of this trailing instruction which created an exception. So, it means like we need to have the support in our processor to deal with this exception scenario. If any processor which has the support for this, then we can say the processor supports the precise exceptions. If a system supports a precise exception, then the system can checkpoint the state of the mission instruction by instruction, so that at any point of time, if any instruction is going to create an exception, we already save the state just before that the exception instruction, so that we can compute without any problem. So, again ROB is going to take care of these precise exceptions, and whenever we execute an instruction which creates an exception, so what we are going to do is all the instructions starting from that exception instruction and all the trailing instructions which are issued starting from that exception instruction will be invalidated, because we have one field in our ROB per entry, that is a valid bit, and we can invalidate the corresponding instructions, so that these instructions are not going to have any impact on the mission state or the process state effectively. So, using our ROB or reorder buffer, we can take care of these precise exceptions. So, with that I am concluding the organization of superscalar processors, and in the next module we are going to discuss another important component in superscalar process, that is register renaming, and we know that register renaming is used for eliminating the name dependencies. Thank you.